Welcome. In this video, we're going to talk a bit about the z-test for comparison of means. So this will look very similar to the z-score formula, but there are some important differences that we should note. First, we are comparing a sample mean to a population mean. So in the numerator on the left, we have the sample mean, and we're subtracting from it a population mean. And basically, we're testing the null hypothesis that the population that the sample mean has come from is equal to the population mean that we're comparing it to. In other words, you can think of it as we're trying to see if they're from the same population or if they're from different populations. In order to do that, we're taking the difference and we're dividing it by the standard error of the mean, which you'll remember is our estimate of how much discrepancy we expect between our sample estimate and the actual population parameter for the mean, the population mean that it's intended to represent. So we're basically taking a measure of the difference between the means and dividing it by the error. And this is going to be kind of a common theme throughout this course, where we're taking a measure of a difference or an effect or a signal, and we're dividing it by a measure of the amount of error or noise or uncertainty. So usually the denominator is our error or uncertainty, and the numerator is a difference that we actually found. And to the extent that the difference is much larger than the amount of uncertainty, we may be able to reject the null hypothesis and claim that there is a statistically significant difference between means, or in other situations, a statistically significant relationship between variables. To the extent that the difference between the means is not sufficiently larger than the amount of error or uncertainty we expect, then we will not be able to reject the null hypothesis and we will not have support for the alternative. The alternative could be a non-directional alternative where we're just saying that the two means are different from each other, or the alternative could be a directional alternative where we're either saying the mean, the sample mean, or the population from which the sample mean comes from is significantly greater or significantly lesser than the population mean we're comparing it to. But in any case, here's the formula: sample mean, subtract population mean, and divide by standard error of the mean. Remember, we can calculate the standard error of the mean by taking the population standard deviation and dividing it by the square root of the sample size. If you have the variance, you can take the square root of the variance divided by the sample size. It's an equivalent, mathematically equivalent formula. So when would we use the z-test? Well, if we know the population mean, or we have some fixed value that we want to compare a sample mean to. So if we know the population mean and we know the population standard deviation, we'll assume it's a random sample. We can basically ask, what's the probability of finding the sample mean that we found, or greater, if the null hypothesis is true? And if that probability is low, if the p-value is low, then we have more evidence against the null hypothesis. Usually we compare the p-value, as you might recall, to alpha. So if the p-value is below alpha, we'll reject the null hypothesis. It gets a little bit more complicated when we're considering whether or not it's a one-tailed or a two-tailed test, but for now we'll just disregard those complications. So basically what we're trying to do here is to determine how unusual or extreme the difference that we found is, assuming that there's no difference at all. So assuming that the null hypothesis is true, how unusual or extreme is the difference that we found? And if the p-value is low enough, we'll reject the null and we'll say that there is a statistically significant difference. And how low is low enough? Well, typically that is below the alpha that was indicated by the researcher or in the problem that you're doing. So once you compute a z-score, and there's a subsequent video which shows the computation of the z-score, once you compute the z-score, you can use it just as you did, the z value you can use it just as you did when we computed z-scores to look up what's the probability of that z-value. So you can use the calculator which is available on Blackboard, and you can, if it's a right-tailed test, you can ask for what's the proportion of the area under the curve above the z value that you computed. If it's a left-tailed test, you can ask what is the probability of getting the z value that you a value below the z value that you computed. If it's a two-tailed test, you can ask for the probability outside the value that you computed, and that will give you the p-value here. So here's a hypothetical p-value of 0.0655, which would indicate if the null hypothesis is true, we would expect these results about 7% of the time. So if our alpha was 0.05, then we would not be able to reject the null hypothesis because the p-value is greater than the alpha. So I hope you've enjoyed that brief explanation of a z-test and how we can use a z-test to compare means and to determine the probability of the results if the null hypothesis, assuming the null hypothesis is true, and decide whether or not we should reject the null hypothesis based on the p-value and its comparison to alpha.